So let's talk about the instrumentation for the dynamic electrochemistry then. Uh, this is going to be a little bit different from potentiometry and whatever electrochemical cells that have work, right? In those cells, you have two electrodes, anode and cathode. Or for potentiometry, we call it indicator electrode and reference electrode, right? But now you have seen that we have some problem in performing dynamic electrochemistry because we have the ohmic drop, right? Potential is kind of hard to fix by this kind of thing. So we're gonna see that we have to fix the ohmic drop problem. And the way to fix the ohmic drop is to use the three-electrode cell. So in the dynamic electrochemistry, we need three-electrode electrochemical cells. So let's see what are those three electrodes. The first electrode is called working electrode, or sometimes we abbreviate it as WE. Working electrode is where the electrode reaction of interest occurs. For example, if we want to, let's say, if we want to reduce copper to iron to copper, that electrode that we are doing the reduction, we call it working electrode. That's the first electrode. The second electrode is the reference electrode, which is our family reference electrodes. That's the same thing. Either silver chloride or standard column electrode. We can use this as the reference electrode. And again, just to review, the reference electrode is used in the three-electrode cell is to measure the potential against the working electrode. For example, from the first example, we have the situation that we apply 1 volt, right, versus silver chloride. So this 1 volt going to be the voltage difference between the working electrode and the reference electrode. In that example, the reference electrode is silver chloride. So these two electrodes actually is pretty similar to what we have done before. But now we have the third electrode, the new electrode. We call it auxiliary electrode, AE, or counter electrode, CE. This is the same thing. You're going to see these two terminologies interchangeably. The role of the auxiliary electrode is to first to complete the circuit, and second, to pass the current through to alleviate the IR drop. You can imagine that if we don't have the auxiliary electrode, we're going to have only the working and reference electrode, and the current will flow through these two electrodes. And if you have the current flow through these two electrodes, you're going to have the ohmic drop or the IR drop. But now, if you can direct the current to flow between the working electrode and the auxiliary electrode instead of the reference electrode, then you can have the accurate readout of the voltage, because now your circuit between the working and the reference electrode will not have the current, which means that you can alleviate or eliminate the IR drop by using the third electrode. So if someone asks, why do we need the three-electrode cell? The main answer is that to alleviate the IR drop. So these are three electrodes. But now you can see that we're going to have to measure or control the voltage, right? And then we're going to have to measure and control the current as well. And the instrument to do this is called potentiostat. Now you don't need to remember the circuit. I just put this for the explanation. But you have to know how does it work? The potentiostat is the instrument to control and measure the electrical parameters. Including here, we know that we're going to have to deal with the potential and the current. The potentiostat will basically have the voltmeter across the working and reference electrode. You can see from the circuit here that the voltmeter is put across the working and reference electrode in order to measure the potential difference. And to measure the current, we need the ammeter. And the ammeter will place in the circuit circuit between the working and the auxiliary electrode. So basically the voltmeter must have very high resistance in order to keep the electron flows out of this circuit. So the electron flows will have itself into this circuit, the circuit of the working and the auxiliary electrode, so that you don't have the IR drop here, and then you can have the accurate number of the voltage. So this is the role of the potentiostat in order to control the experiment in the dynamic electrochemistry. Like by control, we mean to control or to measure the potential and the current. So that's the role of the potentiostat. Another thing that you have to concern is the cell itself. Now you're gonna have the significant amount of the current. So you hope that your cell should be at least more conductive than the potentiometry. So to make it conductive, in your solution, you need supporting electrolyte. This is the electrolyte of the high concentration. For example, maybe 1 molar KCl or 1 molar potassium nitrate. And this supporting electrolyte, of course, will allow the solution conductivity to reduce the resistance. Another role of the supporting electrolyte is that it will prevent the analyte migration. This is a little bit above this level, but I can just tell you that in electrochemistry, we usually want the analyte or the electroactive species to undergo only diffusion, not migration and not convection, because you can control the mathematics so that your calibration curve kind of accurate enough. So by putting the supporting electrolyte, this supporting electrolyte will undergo migration instead of the analyte, so that your analyte can undergo only diffusion, and that will improve your analytical performance or analytical measurement. And in general, you can use this regular ionic salt. But if you are working with the pH sensitive species, so for example, if you want to, let's say, you want to oxidize or reduce ascorbic acid or dopamine, which is pH sensitive. So in this case, you must use a pH buffer, maybe a phosphate buffer, right? If you want to work around pH 7 or pH 6, you use pH buffer. If in acid, you may use the citrate buffer. In the base condition, you may use the ammonium chloride as a buffer, something like that. So basically, if you want to control the pH, then you will replace this typical ionic salt with the buffer. And the buffer is already ionic, right? So it completes by itself. Another little concern is that you may need to remove the oxygen from the system. By doing this, you connect this with the nitrogen gas, and you put the nitrogen tube in this solution, and you push the nitrogen into the system so that the oxygen is kicked out. And why don't we need oxygen? Because oxygen can be reduced in electrochemical cells, actually, because now we are dealing with dynamic electrochemistry, right? And then we want the current to be only from our electroactive species. So if your solution have oxygen, then when you perform reduction, you're gonna see the current from the oxygen reduction, which may interfere our analysis. So we want to eliminate this. And another reason is that maybe some species can be oxidized by the air or the oxygen in the air. So you have to remove the oxygen in order to prevent these two phenomena. So this is basic three-electrode electrochemical cells. You need working electrode, reference electrode, auxiliary electrode, and then a potentiostat to control the potential and the current. And in the solution, you need supporting electrolyte, and sometimes you need to remove the oxygen. So any question on the cells kind of thing? Okay. So this is the diagram. So let's see the actual stuff. This is the actual cell that we have. This is the potential stat. It can be not very large, but it can be large. This is not small. Has the same size of the, let's say, the case, the computer case. This is from Metro, yeah, Outer Lab. So this is the potential stat, and you can connect the potential stat with these three electrodes. The three electrodes now is here, like working counter and reference, and then they are put in the solution to perform the electrochemical analysis. And today you don't directly work with the potential stat, but you connect it with computer or laptop, and then you control and record the electrical quantities through your program, which is very convenient. But this is a little bit large, so so this is why I put it full scale potential stat and electrochemical cells. If we want to perform the dynamic electrochemistry, like maybe outside or maybe at your home, then of course this may be too large. So we can shrink the size. We can shrink the size to be like something like this. This is from the the literature, like this is 2018. They can shrink down the potential stat to this box, which is actually smaller than your hand. These whole things is miniaturized into this, and then your three electrodes now can be miniaturized into screen printed electrode, which can be disposable because this is very cheap, and you can control it through your smartphone. So you don't need the whole laptop. You can just use smartphone, and your potential stat here is wireless, so you can just need the internet to connect between your smartphone and your potential stat. If we zoom in to the screen printed electrode here, you can see that it has the three electrical connection here, which connects with the three electrodes. This the black area in the middle is the working electrode, and this kind of grayish color is of course the color of the silver chloride ink. So this is the silver chloride ink reference electrode, and this black, the outer black here is also the carbon. I think it's the carbon counter electrode. The middle here is the carbon working electrode. And with this instrumentation, you can change the ink to whatever you want. For example, if you know that your compound doesn't work well with the carbon ink, you can change it to maybe gold ink if you have money, something like that. Or if you want to put some enzyme on it, you can do it, obviously. Just put some enzyme and let it dry, and then you can use this as your biosensor. So by miniaturize the device, then you can make it portable. In terms of the material, I want at least I'm not sure if I can rearrange. I can arrange you guys to have the actual lab, because we have limited amount of these instruments in our department. So that's why I put a lot of pictures so that you can see what we are talking about. The actual reference electrode for dynamic electrochemistry is something like this. This is silver chloride, for example. So this is the silver wire, and this should be white, but I don't know what's happened here. So this is silver encoded with silver chloride, and this can be in the glass or this can be in some plastic, depends on your preference. So this is your reference electrode. Your auxiliary electrode. The only two main properties is that it should have large electrode surface area and it should be inert. So again, our inert material is platinum and carbon. So this, if you are rich, you can use platinum rod, but if you don't really care, you can just use carbon rod. In some case, you can even use your graphite or your pencil lead as your auxiliary electrode. Your pencil lead is a little bit fragile, right? But depends on your application. In terms of working electrode, you can see a lot of materials here. You can have like several sizes of the working electrode, but this one I use it choose it to be the same. This is the platinum, this is gold, this is silver, and this is something we call glassy carbon, which is carbon with a specific chemical structure. And the size is around, the diameter is around 3 millimeter. I think this is the zoom in image. So it seems large, but it's not really large. So this depends on your choice of material, which material that you want to work with. And then once you have 3 electrodes, you can connect these 3 electrodes and put into this cell. And again, if you want to be portable, you can do the screen printed electrode, and you can find the ink of this material and screen it on some substrate, like maybe paper, maybe plastic. What else? This is the zoom in of the cell. You can see 3 electrodes here, and then there are some holes to put the nitrogen purging gas. So you connect the line of the nitrogen and keep the oxygen out. Yeah, I didn't show you here because that's gonna be too much. And the screen printed electrode, you can buy it or you can do some kind of homemade. This is one from our department. So you have the plastic sheet, and then you screen the silver ink, and then you screen the carbon ink. So this is 3 electrode. So the feature is similar to this one. It's similar to this. This is the commercial one from the Metro as well, but this is in-house, the homemade screen printed electrode. This is carbon ink, this is carbon counter electrode, carbon working electrode, and this is silver chloride ink for the reference electrode, and then you connect with three connectors. In some case, I want to show you like some technology. We can further miniaturize the electrodes. And this is like my work previously from my PhD. This is carbon fiber micro electrode. Then the size is very small. The diameter of this carbon fiber is only 7 micrometer. So basically smaller than your hair. And people usually use these small electrodes to put it in some animal to study the biological activities of something. Like this is electrochemistry of neurotransmitter. So they're measuring the neurotransmitter in the rat brain. For example, they may let the rat take some drug, like maybe cocaine, or maybe they let it eat something delicious, and they detect the neurotransmitter compound. And these neurotransmitters are electroactive, like maybe dopamine, maybe serotonin. These species can be oxidized, so you can measure the current and then maybe explain the correlation between these neurotransmitters and the behavior of the animals. And because you can see that the animals is small, so to plug this bulk electrode is too large, right? And then the working area is actually the brain, and brain is small, so that's why you need the small electrode like carbon fiber. And like my previous experience is to like modify the carbon fiber to have like more surface area so that you can see more electroactive species and get higher current and improve the analytical performance. Like here I put carbon nanohorn, which is kind of carbon nanoparticles on the carbon fiber, and it improves the properties of the electrodes. So this is like the actual application of the dynamic electrochemistry. The question is that how to choose the material, how we can choose the material. It turns out that first maybe it depends on your preference, and second maybe depends on the potential that you want to work with. So for each system of the working electrode and the solvent or the supporting electrolyte, we have something called potential window. The potential window will indicate the potential range of the electrode solvent that should be used. For example, let's start from the lower part, the carbon. So like carbon in KCl, and this is the this is a potential window of carbon in 0.1 molar KCl, potassium chloride. It means that you should use this system between this potential range. from -1 volt to, let's say, plus 1.3 volt. Because at higher potential, you may have some water oxidation or the oxidation of the electrode material itself. If you use too negative potential, maybe you will cause the reduction of water, or maybe the reduction of the oxygen if you don't want one, or maybe the reduction of the electrode material itself. And this is very, very important for carbon, because carbon can be oxidized and reduced. So if you use too low potential, then it can be reduced and you're not going to get the accurate information. So what if you want to work with some negative potential, like to reduce metal ions? So to reduce metal ions, you may use people in the past use mercury electrode. I didn't have the picture here. So the mercury electrode works well in the negative potential region with several supporting electrolytes, because mercury can form some amalgam with metal ion, and then you can get some decreasing in the activation over potential. But you don't want to use it at the high potential, because mercury obviously can be oxidized as well. So you're gonna get mercury oxide and your electrode is ruined. And platinum, here you can use more positive than the mercury, but as not as good as carbon, something like this.